Imagine a world where particles have evil twins. Not just evil, but opposite in every way. That's the bizarre reality of antimatter. Every particle of matter, the stuff that makes up you, me, and your morning coffee, has an antimatter counterpart. These antiparticles are like mirror images with the same mass but opposite charge. Meet an electron with its negative charge. Say hello to the positron, its positively charged antimatter twin. Protons, the building blocks of atoms, have antiprotons. Even neutral neutrons have antineutrons. But here's the catch. When matter and antimatter meet, they annihilate each other in a burst of pure energy. It's the ultimate showdown, with energy as the sole survivor. So, we live in a universe made of matter, which begs the question, where did all the antimatter go? Stay tuned, because the answer is far from simple. Our story begins in the 1920s, a decade of great scientific exploration and discovery. The world was still reeling from the aftermath of the First World War, and the roaring 20s were in full swing. Amidst the jazz music, flapper dresses, and the rise of cinema, a quiet revolution was taking place in the world of physics. At the heart of this revolution was a brilliant, if somewhat eccentric, physicist named Paul Dirac. Born in Bristol, England, Dirac was known for his deep, almost mystical approach to mathematics and physics. His colleagues often described him as a man of few words, but his equations spoke volumes. Dirac was wrestling with equations that described the behavior of electrons. These tiny particles, which carry a negative charge, were already known to be fundamental components of atoms. But Dirac's equations were different. They were elegant, groundbreaking, and held a surprise that would change the course of physics forever. His equations, elegant and groundbreaking, held a surprise. They predicted the existence of a particle with the same mass as an electron, but with a positive charge. This was a radical idea at the time. The concept of antimatter was not just new, it was almost unthinkable. They predicted the existence of a particle with the same mass as an electron, but with a positive charge. At first, Dirac hesitated. He was a meticulous scientist, and the implications of his equations were profound. Was this a mathematical quirk, or was he truly onto something revolutionary? The scientific community was skeptical, and Dirac himself was cautious. Was this a mathematical quirk, or was he truly onto something revolutionary? Dirac pondered this question deeply. He knew that if his equations were correct, they would not only predict the existence of a new particle but also suggest a mirror universe of sorts, where every particle has an antiparticle counterpart. He cautiously proposed the existence of this anti-electron, which we now call the positron. This was a bold move, and it was met with a mixture of intrigue and skepticism. The idea of antimatter was so foreign that many scientists found it hard to accept. Yet, Dirac's mathematical rigor could not be easily dismissed. Dirac's prediction was met with skepticism. The scientific community was divided. Some saw the beauty in Dirac's equations, and were willing to entertain the possibility of antimatter. Others were more cautious, demanding experimental evidence before they would accept such a radical idea. After all, no one had ever seen an antiparticle before. The concept was purely theoretical, and the technology of the time was not advanced enough to detect such particles. Dirac's ideas were ahead of their time, and it would take a few more years before they could be tested. But Dirac, ever the theorist, stood by his equations. He believed in the power of mathematics to reveal the secrets of the universe. And he was right. His unwavering confidence in his work would soon be vindicated. Just a few years later, in 1932, American physicist Carl Anderson made an astonishing discovery while studying cosmic rays. Anderson was a young, ambitious scientist working at the California Institute of Technology. He was using a cloud chamber to study the paths of cosmic rays, high-energy particles from outer space. He found evidence of a particle that behaved just like an electron, but curved the wrong way in a magnetic field, indicating a positive charge. This was the first direct evidence of the positron, the particle that Dirac had predicted. Anderson's discovery was a monumental moment in the history of physics. The positron had been found, vindicating Dirac's bold prediction and opening a new chapter in our understanding of the universe. This discovery not only confirmed the existence of antimatter, but also paved the way for future research into the fundamental nature of the cosmos. The antimatter genesis was just the beginning of a journey that continues to this day, as scientists explore the mysteries of the universe and the role that antimatter plays in it. Following Anderson's groundbreaking discovery of the positron in 1932, the hunt for antimatter intensified. This discovery was a monumental step in the field of particle physics, opening up new avenues of research and sparking the curiosity of scientists worldwide. Physicists soon realized that cosmic rays, those high-energy particles bombarding Earth from space, were a natural source of antimatter. These cosmic rays, originating from distant galaxies and supernovae, provided a unique opportunity to study antimatter in its natural form. Observatories around the world began capturing images and data, revealing the mysterious nature of these particles. However, studying these elusive particles required more controlled environments. The unpredictable nature of cosmic rays made it difficult to conduct precise experiments. Scientists needed a way to recreate these high-energy conditions in a controlled setting, where variables could be meticulously managed and outcomes accurately measured. Enter the particle accelerator, a physicist's playground for smashing particles together at incredible speeds. These massive machines, some spanning several kilometers, became the new frontier for particle physics research. By accelerating particles to nearly the speed of light and then colliding them, scientists could simulate the conditions of the early universe moments after the Big Bang. By colliding protons and other particles at nearly the speed of light, physicists could create miniature Big Bangs, briefly producing antimatter particles in the process. These collisions generated extreme energy densities, allowing for the creation of particles that would otherwise be impossible to observe. The data collected from these experiments provided invaluable insights into the fundamental building blocks of the universe. These experiments confirmed the existence of antiprotons, antineutrons, and even antiatoms, albeit fleetingly. The detection of these particles was a testament to the precision and ingenuity of modern scientific instruments. Each discovery brought us one step closer to understanding the true nature of antimatter and its role in the cosmos. Antihydrogen, the simplest antiatom, was created and studied in labs, its properties meticulously compared to those of ordinary hydrogen. This comparison was crucial, as any differences could provide clues about the fundamental symmetries of the universe. Researchers developed sophisticated techniques to trap and study antihydrogen, allowing them to measure its properties with unprecedented accuracy. The more we learned about antimatter, the more questions arose. Scientific conferences and discussions became hotbeds of debate and speculation. Why was there such an apparent imbalance between matter and antimatter in the universe? What mechanisms could explain this asymmetry? These questions drove researchers to push the boundaries of their experiments and theories. Where was all the antimatter in the universe? This question puzzled scientists and led to numerous hypotheses. Some suggested that antimatter might be hidden in distant regions of the cosmos, while others proposed that it could have been annihilated in the early universe. The search for answers continues, with new experiments and observations constantly refining our understanding. Could we harness its incredible energy potential? The annihilation of matter and antimatter releases enormous amounts of energy, far surpassing that of conventional chemical reactions. This potential has led to speculation about its use in energy generation, offering a tantalizing glimpse of a future where antimatter could power our cities and technologies. And could it be, as science fiction suggested, the key to interstellar travel? The idea of using antimatter as a propulsion system for spacecraft has captured the imagination of scientists and writers alike. Such a system could theoretically achieve speeds close to that of light, making interstellar travel a possibility. While this remains a distant dream, the ongoing research into antimatter continues to inspire and challenge our understanding of the universe. Here's a cosmic conundrum. If matter and antimatter annihilate each other on contact, and they were created in equal amounts in the Big Bang, why does any matter exist at all? This question has baffled scientists for decades, leading to numerous theories and experiments. Shouldn't the universe be a vast, empty sea of energy, the aftermath of a cosmic matter-antimatter free-for-all? Theoretically, the universe should have been left with nothing but energy after the mutual annihilation of matter and antimatter. Yet, here we are, surrounded by matter, with nary an antimatter galaxy in sight. This apparent imbalance is one of the most intriguing puzzles in modern physics. It seems the universe has a slight preference for matter, a bias that has puzzled physicists for decades. Theories abound, each trying to explain this cosmic mystery, suggesting subtle differences in the behavior of matter and antimatter that gave matter a slight edge in the early universe. Some theories propose that during the first moments after the Big Bang, tiny asymmetries in the laws of physics favored matter over antimatter. Perhaps antimatter decays slightly faster than matter, or maybe there are unknown forces at play. These forces could have influenced the balance between matter and antimatter, tipping the scales in favor of matter. This matter-antimatter asymmetry is one of the biggest unsolved mysteries in physics. Understanding it could revolutionize our comprehension of the universe. Solving it could hold the key to understanding the very fabric of our universe. It might reveal new physics beyond the standard model, offering insights into the fundamental forces that govern everything. Until then, we're left with a universe dominated by matter, with antimatter relegated to the realm of high-energy physics experiments. These experiments, conducted in particle accelerators, aim to recreate the conditions of the early universe and study the properties of antimatter. And of course, science fiction. Antimatter has captured the imagination of writers and filmmakers, often depicted as a powerful and mysterious substance with the potential to unlock new technologies or cause catastrophic destruction. In reality, harnessing antimatter as an energy source remains a distant dream. The challenges of producing and storing antimatter are immense, but the potential rewards drive ongoing research. As we continue to explore the cosmos and delve deeper into the mysteries of the universe, the question of where all the antimatter went remains a tantalizing enigma. Perhaps one day, with the combined efforts of scientists around the world, we will uncover the truth behind this cosmic puzzle. Until then, the search for answers continues, pushing the boundaries of our knowledge and expanding our understanding of the universe. The journey to solve the mystery of matter and antimatter is a testament to human curiosity and our relentless pursuit of knowledge. It reminds us that even the smallest particles can hold the secrets to the grandest questions of existence.